Hello, and welcome to a prep video for 607-181 Hydrology and Conservation. This one dealing with an introduction to open channel flow. If we have a pipe as such, and we'll take this tube for example. There's a little paper tube, but there's a pipe inside that tube. What we know is that Q in must equal Q out. So whatever I put into this end right here, because water is assumed not to be compressible, it doesn't compress. So whatever we put into this end must come out that end over here. In terms of a general outline then, we know that Q is a function of two things. One, the velocity at which it's coming in, and the cross-sectional area which it covers. So it's going to be a function of velocity and area. So in this case, Q in must equal velocity in times my area in, and this would Q out must equal velocity out plus area out. What does that factor in? Well, what this is saying is if we have a pipe that's necking down like this, correct? And we're still putting stuff in, the question is, what's coming out? A hose, the end of a hose. So let's take a look at this. Let's say this is 6-inch diameter and it necks down to a 0.5-inch diameter. My Q in must equal my Q out. So if I say my Q is 10 CFS, 10 cubic feet per second, what is my values? Well, my area here, right, area in, is equal to pi over 4 times 6 inches squared. So my area, or 6 inches, which would be 0.5 feet squared. So that is equal to pi divided by 4 times 0.5 squared equals 0.1963 square feet. And my area out is equal to pi over 4 times 0.5 divided by 12, which is equal to 0.04167 feet in diameter. My area out, 0.416, oops, how about 0.04167 squared. So my area out is equal to, square that times pi divided by 4, 0.0013635 square feet. So if Q equals VA, and my Q was 10 CFS, 10 cubic feet per second, times my velocity, times my cross-sectional area, 0.1963 square feet. This tells me that my velocity here, 10 times 0.1963, is 1.96 feet per second. That's the velocity of the water going in. So what is the velocity of the water coming out? So Q equals VA. Once again, we have 10 CFS, because what goes in must come out, equals my V out times 0.001363. So my velocity out, my V out, would actually equal 7,334 feet per second. Significantly higher in terms of cross-sectional diameters necking down. You can see the effect of the dramatic increase of velocity. And this is what happens to a garden hose. Your garden hose has a certain diameter coming in, and then you neck it down to a point for the outlet, and thus you're able to spray a lot faster. The question is, how do we get this pi over 4 stuff? We know that area is equal to pi r squared. That's what they always teach us in grade school, where r is the radius. So this right here would be r, and this right here would be my diameter. In our profession, our pipes are typically done in diameters. They're not done in radiuses. So therefore, we know that r, 2r is equal to a diameter. Therefore, a diameter is equal to r over 2. Oops, wrong way. So radius is equal to diameter over 2. I plug that back in, so r equals pi times the diameter over 2 squared. So area would equal pi times diameter squared over 2 squared, which equals pi times diameter squared over 4, and thus we end up with the equation of pi over 4 times diameter squared is our area for a circle. So this is area of a circle based off of the diameter. And we've seen how we can calculate Q equals VA, which is our major equation right here. Q equals VA doesn't have to be just for a pipe. Let's talk a square box cross section. Now let's say our depth of water in this box is 2 feet, and we have a width down here of, say, 3 feet. If the velocity of the water, if the velocity is flowing at 2 feet per second, what is my Q value for this situation? Well, I know that Q equals VA, so my area is going to be 3 feet times 2 feet, which is 6 square feet. So my flow through this pipe, through this section, is going to equal 2 feet per second times 6 square feet, thus equals 12 CFS. And this is how they go about doing measuring stations across dams or waterways. They'll have a section, and they'll actually have a notch in it, a weir, at which they're going to measure the depth of water coming across this. So they'll measure the depth. They already know the width, and they measure the velocity of the water coming across. And out of this weir, they can figure out the flow based off of these two parameters by measuring the depth and the velocity. They can figure out the flow of water across this section, whether this is in a natural channel or across the dam. They can figure out how to make this flow across this system. And realize this symbol right here is called a free water surface. Free water surface. And what we're assuming with this is no pressure. And we'll get into pressurized conditions later. This is talking about a no pressure system. The system isn't under pressure, which isn't, I mean, that's a free water surface. So, let's do another one. Let's talk, we have a pipe like this, and let's say these are 2-to-1 slopes, and we have a bottom here of 3 feet. And let's put the water depth in here at 1.5 feet. And the velocity coming through this pipe, or through this, the velocity is equal to 4 feet per second. What is my Q? So on this cross section, we got to figure out the area now. Well, if we look, if this is my width, right, then my top surface is going to be what? Well, this is my width, and actually let's draw this a little bit more to scale since it's 2-to-1. Here's my width, and we go up 1 and over 2, right? So 2-to-1 slope means we go up 1 and over 2 for our slope. I'm going to put that down here. So we go over 2 and up 1. So we go over 2 and up 1. And if my depth is up here at 1.5, right here, not drawing to scale, let's draw this a little bit better to scale. So here it is, channel, channel, and my depth right here. So we know this is my W, my width, correct? And I know this is go over 2 and up 1. Change that property to gray. So if I come straight up here, right, and this right here is my depth, D, then I know that this length from here to here is W, right? And I know the length from here to here, so the length from here to here is my same as my channel bottom, and my length from here to here is going to be D times my grade, right? So if it's 2-to-1 grade, 2-to-1 slopes, sorry, let's do D times S. So it's D times my slope. Actually, I don't want to use, let's use grade. So D times my grade right? And if this was 2 to 1, it'd be that. And over here, we have d times my grade. So this overall here to here is equal to what? This is W plus 2d times my grade. Those are 3 to 1 grade, 2 to 1 grade, what have you. In our case, what is that? So if this is 3 to 1, what is this distance right here? This would be 3 plus 2 times my depth, which is 1.5, times my side slope, which is 2. And that water width up top, the spread, this is called a spread. And therefore, my spread is equal to 2 times 1.5 plus 3 is equal to 9 feet wide. So my spread is 9 feet wide. Now we got to figure out what is my volume. I mean, what is my cross-sectional area of this water? Well, we know if it's a trapezoid, for any standard trapezoid, W1, W2, and this is my depth. So my area would equal 1/2 times W1 plus W2, the average of those two, times my depth, is the area of a trapezoid. Now in our case, W1 and W2, we can substitute that. So area is equal to 1/2 my width, which is W1, plus the quantity W plus 2 times D times G, correct? That's W2. This is W2. This right here is W1. So therefore, I substitute those in, times my depth. So my area would equal 1/2 times 2W plus 2dg times my depth. And all I've done, I've combined W plus W to form 2W. I'm going to factor out, because I have a 2 and 2 here, that equals 1/2 times 2 times W plus dg times d. And all I've done is factored out the 2, and thus we can cancel this with that. And my area is equal to WD plus D squared G. And if you find this equation in some textbooks, this is where it comes from. That's where the equation actually comes from for that area. WD plus D squared G is this progression from this formula, and this is for a trapezoid. Now let's see if it actually holds true. So in our case, we have two equations, and let's compare them. Let's see if it's actually true. So we have this one, copy, paste, and we have this equation, copy, paste. Now let's just see if they come up with the same value for our cross-section. So right here is our cross-section, maybe. Should group us one of these days. There we go. And so here is our value. Let's see if we get the same exact number then for these different pieces. So in our standard trapezoid equation, area would equal 1/2. My W1 would be 3, plus my W2 is 9, times my depth, which is 1.5. So this would equal 12 divided by 2, 6 times 1.5 gives me 9 square feet. What about over here? Area is equal to W, which is 1.5. No, I'm sorry, 3. My W is 3. 3 times my depth, which is 1.5, plus D squared, which is 1.5 squared, times my G, which is 2. For anybody keeping track, this right here is basically this area right here in terms of where the pieces are coming from. And this area right here is these two sections out here. And notice there are two triangles, and when we take the two triangles, it becomes a square. So 3 times 1.5 gives me 4.5, plus 1.5 squared, 1.5 squared times 2, which is 4.5, and thus we get the same area, 9 square feet. So indeed, these two equations are exactly the same. A lot of the hydrology textbooks will use this equation because of the parameters that are given. This way we don't calculate the spread, we just use the bottom channel width, we use the depth, and we use the side grades to calculate the value of our flow. So two equations that give us the same area for a trapezoidal channel. Do they apply for a V channel? Here's my V channel, and here's my depth, right? So here's my depth. Now let's say these are 3 to 1. So 3 to 1 and 3 to 1. And let's say our depth is 2.5 feet deep. What's the area? Well, my base right here, what is my width? My width is 3 to 1. So I take 2.5 times 3. This is 7.5, and this is 7.5 for a total of for a total width of 15 feet wide is my spread, right? And so I know the area of a triangle is 1/2 base times height, which would be 1/2 my base being 15 feet and my height being 2.5 feet. So my value becomes 15 times 2.5 divided by 2, which is 18.75 square feet. So that's for a triangle, but our equation should still work. If we mathematically developed it correctly, this equation should work even for this condition. So I'm going to paste it over here. And where are our parameters? Well, my width of my channel is 0. My depth is 2.5. And my side grade is 3 to 1. So my area is equal to 0 times 2.5 plus my depth, which is 2.5 squared times 3. So 2.5 squared times 3 gives me an area of 18 0.75 square feet. And thus, this is the equation, once again, that you see for an open channel flow. In terms of this now, let's try one more. So let's say we have a 5-foot bottom with a flow of 0.8 feet, and we have a grade of 4 to 1. What is our value for the area in this flow parameter? So let's go back. We'll get our equation, copy, since we know it works. So our width, our bottom width was 5. Our depth is 0.8 plus 0.8 squared times 4. So therefore my area is equal to 5 times 0.8 plus 0.8 squared times 4, 6.56 square feet. Double check that, 5 times 0.8, 0.8 squared times 4 plus 4 is 6.56 square feet. So this cross-sectional area is 6.56 square feet. We talked about Q equals VA. And we know how to calculate Q based off of whether we do Q equals CIA, which is the rational method we've talked about so far. There's a couple other ways of calculating Q that we saw off the DOT. We now know how to calculate A for a cross-sectional area. The question is, how do we calculate V for an open channel? Velocity for an open channel, meaning that we have a free water surface, there's no pressure in the system. The velocity for an open channel in English units is equal to V, which is equal to 1.49 divided by the roughness of the pipe. So it's going to be a function of how rough this pipe is, right? The rougher the pipe, the slower the velocity. The smoother the pipe, the faster the velocity. Thus, it makes sense that we divide it. Times what we call the hydraulic radius to the 2/3. And the slope, the longitudinal slope of the channel to the 1/2. The hydraulic radius, what is that? Well, in any channel, your friction always occurs, here's your water, your friction always occurs where you have contact with the material, right? That's going to be a friction. So the more friction area you have over the area, the more friction area you'd have over a given area, the slower the water is going to be. So the hydraulic radius is going to equal my area divided by what we call the wetted perimeter. The wetted perimeter. So this wetted perimeter is the key. Back to our piece then, we have an area right here, right? We've developed the area calculation for this. So I want to copy this, paste this up. So we've talked about the area, but how do we get the wedded perimeter? So what about our wedded perimeter? And well, we know a function is going to be 5 feet, right? So my WP has to equal at least my width, correct? My width right here. So we start off, we know it's going to be the width. And now we got to figure out this length right here. How do we figure out that length? Well, we know that this right here, this is my depth. And this is going to be my depth times my grade, correct? We've looked at that before. So the hypotenuse is equal to, d squared plus the quantity dg squared, taking the square root. So the hypotenuse is equal to the square root of d squared plus d squared g squared, correct? And let's move this up, shrink this down a little bit. Which we can rewrite as the hypotenuse is equal to the square root of d times 1 plus g so d 1 plus g times d squared. So just factoring that through, we got 1 plus g times d squared, and then we got two of them because we got one on this side and one on that side. So my wedded perimeter is going to equal plus 2 times the square root of 1 plus g times my depth squared. Let's find out if that's true. So using this as our example, let's find out if that equation holds true. We know this has to be 5 feet right here. This length right here, since it's 4 to 1, my depth is 0.8. 0.8. My width, we figured out before, was what? So if we look up here, my width right here is going to be 0.8 times 4, which is equal to 0.8 times 4, which is 3.2 feet. And so my slope right here, this portion of my wedded perimeter, right through here, is going to be 3.2 squared plus 0.8 squared equals square root. This length is 3.298 feet. So that length is 3.298 feet. So we know that it should be 3.298 plus 5 feet plus 3.298 feet for a total of should be around 11.596 feet for my wedded perimeter. Let's see if the equation provides that to us. So my wedded perimeter is going to equal 5 feet plus 2 times the square root of 1 plus 4 times my depth, which is 0.8. So 5 times 0.8 equals square root times 2 equals plus 5 equals 9. Shoot, I screwed up my equations. Yes, I messed up my equations. Look at this. This is g squared. So that needs to be g squared inside, because this is a 1, this is g squared, so that has to be g squared in here. So let's see if we get the right equation now. So I get 1 plus 4 squared times 0.8 squared. So 4 squared plus 1 times 0.8 squared equals 10.68. I take the square root of that times 2 plus 5, and I end up with a wetted perimeter of 11.597 linear feet. So indeed, now we got the right equation. This is the equation that you'll see for the wetted perimeter of a trapezoid, where this is the area. My wetted perimeter is equal to W plus 2 times the square root of the quantity 1 plus my grade squared times my depth squared. So that's the equation for my wetted perimeter. And thus, my hydraulic radius is equal to the area divided by my wetted perimeter. So let's go through and see if we can make this make sense. If I have a trapezoidal ditch and I have a depth in it, let's say of, let's call this 2.5 feet. And I have a width of 4 feet, and I have a slope of 3 to 1. I want to know, and I have a longitudinal slope of this channel. My longitudinal slope is, let's say, 0.86%, and it's concrete. What does that mean? Well, let's look it up. I'm going to www.google.com. I'm going to look up Manning's roughness coefficients. So Manning's roughness coefficients. And here's the roughness coefficients for a variety of different materials. You'll notice that when we start talking concretes, 0.012 is a typical, or 0.13. When you start talking corrugated metal, 0.22, 0.022 to 0.024. I like personally using 0.024 for corrugated metal and 0.012 or 13 for concrete. But you have a bunch of different values, and as you can see, the values change depending on what the material is. The rougher the pipe, the higher the Manning's roughness coefficient. The lighter the pipe, the lighter it is. And so if we look on down in here to polyethylene, look at this value right here. Polyethylene can drop to 0.009. So you could have a 0.012 concrete pipe, line it with polyethylene, and you can drop that to a 0.009 if you do a very smooth inside wall. We'll get into that coming up. But this is your roughness coefficients in terms of what you're looking at. So if we have a concrete channel, and let's just assume this is an RCP channel running at a 0.012 roughness. What would be my velocity? Well, first I need to figure out, first I need the equation. So I know that velocity is equal to 1.49 divided by n, hydraulic radius to the 2/3, my slope to the 1/2. We have the slope given to us. We have the roughness coefficient given to us. So what we need to figure out is the hydraulic radius, which is my area divided by my wetted perimeter. My area for this, if we go back to our open channel flow and we copy this over, my area is going to be this. And if I go back and I get my wetted perimeter, which is right here. So therefore, my area is equal to 4 times my depth, which is 2.5, plus my depth, 2.5, squared times my slope, which is 3, which gives me an area of 2.5 squared times 3 plus 4 times 2.5, 28.75 square feet. And my wetted perimeter, well, I don't want that one, I want my wetted perimeter. So I'll move the wrong one. Let's move this one up to here. This is what we know we need. So delete that. And my wetted perimeter is equal to W, which is 4, plus 2 times the square root of 1 plus my G, which is 3 squared, times D, which is 2.5 squared. So this is equal to 4 plus 2. Well, let's go through and figure that out. So I take 9 plus 1 is 10 times 2.5 squared equals, take the square root of that, times 2 plus 4 is equal to 19.81 linear feet. If you have a question on that, is that actually true? Let's check it. So, all programs, Autodesk, English. We'll let this load. So, we have Autodesk loading up here. And I'm going to come up here and say get new layer, layer manager, layer manager. I don't want the exchange. Well, thanks for the offer. So I'm going to come up to layer manager. And I'm going to create a new layer called trapezoid. Make it current. So then I'm going to draw a line from 0, 0 to how wide was our channel? We were 4 feet wide. So then I'm going to draw a line. I'll just draw a line from here at 4, 0. So I have a line at that direction. And then I want a line from the end point right here. I'm going to go at 3, 1. So I'm 3 over, 1 up. as such. I'm going to go a line from the end right here at -3, 1. So I have my pieces like that. I'm going to offset. My depth was 0.8, correct? So my depth, was it 0.8? No, my depth is 2.5. Take that back. So I'm going to erase this. So offset 2.5 feet from here up. And then I'm just going to type, it's, come on. So I want to connect it, but it's CH, no, not a circle, CHAMF here. There we go. And my value is that. So I'm going to select my first line, which is here, my second line there, and they connect up. Once again, this line to that line, and we connect up. Now, I want to have P line, right? P line. I'm going to pick, how about P edit, polyline edit. I'll pick this line. Do I want to turn it into a polyline? Yes. I'm going to join now this one and this one, because that now becomes my wedded perimeter. So by joining them, now I can list this line right here, and I find out that length is 19.81, and we calculated 19.81 linear feet. Also, now I'm going to make another layer called area, and make this current. And now I can type, actually, area, we're going to make that color, let's just make it pink. Nah, about nice green. It's okay. And then in a B poly command, and I'm going to pick a point inside, right there, enter. And now I have a polygon on this area, and when I list this polygon, it tells me my area of 28.75. Is that what we had? 28.75. So you can quickly check your stuff in AutoCAD with regards to your area and web perimeter. And so we've calculated by hand. So now we know my hydraulic radius is equal to area divided by web perimeter, which is equal to 28.75 divided by 19.81, which gives me a hydraulic radius of 28.75 divided by 19.81 of 1.4513 linear feet. And then I know that my velocity is going to equal this value. So my velocity is equal to that. Therefore, it's equal to 1.49 divided by 0.012 times my hydraulic radius, which is 1.4513 to the 2/3, times my slope, 0.0086. Notice this was in percent, and I need to convert that to decimal, 0.0086 to the 1/2. So my velocity of this section through this section is going to be 14.76 feet per second. We already know the area is equal to 28.75 square feet. So the Q at this slope, the flow of water through this channel at this slope, giving this aspect, is times VA. So the flow through this channel is actually 424.4 CFS. So we can calculate how much flow is actually flowing through this channel given these parameters. It doesn't have to be just a channel. Let's take a pipe, and we'll say this pipe is a 36-inch CMP pipe. So it's a 3-foot diameter pipe, and we're flowing half full. And on top of that, we have a situation where the slope is a 1.2%. So here's my water line. I know this is where I'm flowing. So my area is going to equal 1/2, because it's half the pipe, pi over 4 times diameter squared. So my area, 36-inch pipe, is a 3-foot pipe. So my area is going to equal pi divided by 4 times 3 squared equals divided by 2. So my area is 3.53 square feet. My wetted perimeter is my circumference right here. And my circumference for a circle is equal to pi times diameter. But in this case, we have half a circle, so that'd be 1/2. So 0.5 times pi times my diameter, which is 3. So that's 4.713 linear feet. And let's check it, see if that's true. Are these the numbers we actually wanted? So I'm going to take this and delete it. Oh. Okay, we got to come up here, layer manager, and all these now come that way because it's using the smart cart. Typically, this only happens when you use a smart cart. So I'm going to draw a circle right here at 1.5. My diameter of 3. So there's my 3-foot diameter pipe. I'm going to draw a line from the center of this pipe, the center of this pipe, and coming out flat, so at 4, 0. I'm just going to extend that over and trim that. Now, since this is my water area, I'm going to trim the upper half of my pipe. And so now I can list this, and I can see my radius, my length of 4.7124, 4.713, my web perimeter. Absolutely true. And if I do a B poly, and I pick a point inside here, and then I'm going to list this polygon that I just created. I have an area of 3.53 and a perimeter, but this perimeter includes my line that comes across from here to here, which is not my web perimeter. So the area is 3.53, which we got that right. So my hydraulic radius is area divided by web perimeter, which is equal to 3.53 divided by 4.713, which is equal to 0.75 if we'd round it correctly. So that's my hydraulic radius. So my velocity is going to be 1.49 divided by my roughness coefficient. For CMP pipe, my manning was 0.024. So 0.024 times 0.75 to the 2/3. My slope, which is 0.012 to the 1/2. So I have 0.012 times 0.75 1.49 divided by 0.024 gives me a velocity of 5.61 feet per second coming through here. Thus a Q, which is equal to VA, and we have Q equal VA, so I have 5.61 times my area of 3.53. The flow flowing through this pipe is going to be 19.82 CFS. So we have the ability to calculate our wetted perimeter, our area for a variety of different shapes and sizes. And if you need to, you can draw it in AutoCAD right here and calculate those parameters. And then based off of those parameters, we know this is my geometric parameters, this is my longitudinal parameter, this is my pipe roughness. We can figure out the velocity, and thus Q flowing through each open channel section. So we've done it for a pipe, we've done it for a trapezoid. V-channel is just a unique example of a pipe, of a section. There we go. And so we have the ability to calculate these for different parameters on different pieces based off of open channel. And open channel strictly means that we have a free water surface. We have no pressure inside our system. And make sure you print this out, find it. It's a variety of different spots on the internet, but these are the values for the roughness coefficients that we will be using throughout this semester. And I'll give them to you for other pieces. So, in short, this concludes, we'll get back there. This concludes our open channel flow, where we determined Q, we determined V, and we determined area and a wetted perimeter. 4 major pieces that we obtained to determine our open channel flow for our sections. Thank you.